photograph than I could ever draw or paint. But there's no fulfillment that can be obtained like the fulfillment of taking a blank canvas and actually creating something, actually drawing or painting my own painting or my own drawing or sketch. And that's what this really is all about. Sure, today, in this day and age, unlike when I grew up, you can go buy a laser anywhere. You can buy the little pointers that put the green dots out and make little lines through the air, and it's beautiful and it's wonderful. But to me, the fulfillment comes from actually building a laser from basic parts. And it just so happens there's a type of laser that you can build from the most basic imaginable raw materials that then you could, I mean, it's basically the most simple thing that you could possibly build. What makes that possible is that this laser has an extremely high gain. It requires no mirrors. Now, to give you an idea of what a normal laser is like, with a normal laser, you, at least traditionally, not the kind that are in pointers and that sort of thing, but lasers that existed before the pointers were around were usually a gas inside of an enclosure, or they had a crystal like a ruby, and you had mirrors on both ends. And the medium, that was called the medium, the gas or the ruby crystal or whatever it was used. In some cases, it was even a dye that was contained inside of a chamber. But that medium would be excited by a powerful source of energy. And the energy would then excite the atoms to such an extent that you had more electrons in the upper level than you did in the lower levels. It was what's called a population inversion, and it was necessary for lasing. And once the population inversion was achieved, then what happens, and if you remember from basic chemistry, basic physics, as an electron is excited in an atom and then it returns to the lower state, it releases energy in the form of a photon in some cases, and sometimes it can release the energy in other forms such as heat. Well, when it releases a photon and you have most of the atoms in that upper state, then what happens is the photon stimulates the emission of identical photons, and what you essentially have is cloned photons. You see, a laser is a device that produces all the photons that travel in the same direction, in the same phase of the same wavelength, and that has some very unique properties. And so what makes our little laser here unique is that it has such an enormous gain that it doesn't require any mirrors like most lasers out there do. Any laser you're ever going to see requires mirrors. It's an extremely complex device. But here's a laser that you can actually build from some of the most basic materials that you can possibly conceive. And now I would like to do a little demonstration right now, and I'm going to try to see if I can switch the camera around to the front. First, I've got to plug this in. I'm going to do a demonstration, then I'm going to explain where you can get the parts, what it's comprised of in terms of parts. Okay, this is the laser right here. Now, what you're looking at are called saddle thresholds. They're little bitty metal strips. I think they're the kind of things you would see down at the base of a door that you can buy in a home improvement store. And then what I have is a right-on transparency. And I know you can't see it here, but it's an actual thin film that's only a few thousandths of an inch thick. And they're called right-on transparencies. And the right-on transparency separates a metal plate. And I actually took a beware of dog sign or something you buy in a store. I actually took one of those signs and made the plate out of that, but you can actually use aluminum foil. But then I sanded these little edges around the inside right here smooth, and then I faced those two inside edges together and created a small groove. And what happens is when you generate high voltage and you put the positive side up here and you put the negative side down there, the high voltage discharges through this spark gap. And when the high voltage discharges through the spark gap, you get an extremely fast discharge in this little narrow, think of it like a spark gap that's a long, slender groove instead of like what you think of as when you think of a spark gap, you think of two little balls. Well, think of this as a long, narrow spark gap. Now, the beam is totally invisible, and this is not an optimized design. I don't have nitrogen gas in it. It is working on the ambient air in the room. So this is a proof of principle device. I mean, it's strictly to illustrate the principle and what's actually theoretically possible. But since the beam is invisible, you can't see it. However, it's ultraviolet, and you can see the fluorescence that is generated whenever that invisible beam strikes a fluorescent target. Allow me to illustrate, and I hope you can see this. It's pulsed. Can you, I don't know if you can see the spot forming right there or not, but
yes, we can.
Yeah,
can
we
you
can.
see it?
Yeah.
Yes.
Okay. And because this is fluorescence and not the actual beam, I hope y'all can still hear me.
Yes.
Okay. Then the color is going to change based upon what target material I choose. This one will be blue. And this one right here finally should be green. But in all cases, as the laser fires, and to give you an idea, I can put this further back and you can tell it's a laser because you have a beam with very low divergence coming out of there. I don't know if you can see it from there.
That one. Now the light we're seeing, the bluish light, that's the spark gap, right? And then that's the laser beam we're seeing there.
The laser beam is the thing on the piece of paper.
Right. And the
Yes.
spark gap.
The spark gap, I did move it over the spark gap momentarily for you to see that. Okay. But I hope that everyone could see that. I know it's not what you're used to seeing when you think of a laser. And the reason why is because most lasers you see operate continuously. They're like a flashlight. You flip them on and they put a continuous beam out. This laser right here, however, what you're doing, if you remember from school, energy is power divided by, power is energy divided by time. So what you do is you don't have a lot of energy right here. You have a high voltage source. You're charging these small capacitors up. They're little more than static electricity type size capacitors. But because the discharge takes place in 800 picoseconds, that's 0.8 nanoseconds, or to give you an idea of what that's like, 1 nanosecond is to 1 second what 1 second is to 30 years. So you see, you're discharging that energy in such a small frame of time that you get a tremendous amount of peak power. And I've got some YouTube videos where I explain this in some detail. If you care to look, homemade nitrogen laser, the quintessential type of laser that you can build at home. And I cover this in more detail in my videos. Plus I have my own website that you can check out as well, where I cover some of the other laser types I built. But a laser like this can be built from almost nothing. And I've got videos as well as my website that gives a lot more useful detail about it. But this particular laser right here, what I did to get the high voltage power supply is I went on eBay, and for about $3, you can get these little high voltage generators, is what they call them. They're little high voltage modules, and you can put 3.6 to 6 volts in one side DC, and you get thousands of volts out the other side, and they cost almost nothing. And to give you an idea of what I did here, now part of the advice I got on this was from Sam Goldwasser, but this is one of the power supplies right here. You can see it's extremely small. Well, I put some resistors between the output and some little inductors, little wire round inductors, so that when this capacitor fires, if there's any kickbacks of high voltage, it won't damage the power supply, because if you connect the power supply directly to the laser, you do stand a chance of killing it. And you can run this directly off of batteries. I've got a YouTube video where I show that just running right off flashlight batteries, but it does drain power pretty fast. That can kind of get to be expensive. So I'm actually running it off of another power supply that plugs in. But nevertheless, the laser is very simple to build. And if you want to build one, you can get a power supply like this on eBay for next to nothing. And the spark gap in this case is little brass acre nuts. And I've constructed this little box. and they just connect across one of the top plates and the bottom plate there. And then when the voltage gets to be enough, it discharges between those little balls right there. And when it does, that's when the laser occurs between these gaps. However, you don't have to go through that much trouble. Can you still see me?
Yes.
Okay. You don't have to go through that much trouble at all. You can just lay two little bolts with little anchor nuts right on top of the foil there, and it'll actually work. It's a lot simpler to build one of these even than the one I've shown right here. And so if you care to build one, like I said, you can look at my website, you can look at some of my videos, you can go online. There's many, many examples that are even simpler than the one I've made. But this one here, like I've said again, it's just a proof of principle device. And I've got a couple of drawings here I would like to show you that kind of show you what you're looking at there, since it's not apparent from just looking at the actual finished device. But the way this device basically works is it's called an LC inversion circuit. And I don't know if you can see the drawing or not.
Yeah.
But basically what you have is you have a dielectric, which is an insulating material. I mean, I even got packaging tape to work one time, but it didn't work that good. But you have an extremely thin plastic, and that plastic separates a metal plate on the bottom and two separate metal plates on the top. Can you see okay?
Yes.
Okay. And trying to see if I can get something to point this, no pun intended, but see if I can find something I can point with. Well, let me see. I get something right here. Okay. So what you have right here, you see, is you have this thing right here, and it's the dielectric, and you have a metal plate on the bottom, and you have two separate metal plates on the top. Well, the two top separate metal plates are separated or are connected by an inductor. That's that little springy looking thing you saw on the top, if you recall that. And what that enables the laser to do is for both of these separated sides on the top to charge up at the same time. So you basically got a capacitor, a plate capacitor. Remember your basic capacitors in electronics. You've got a plate capacitor with one of the plates that's split down the middle. And the channel forms that part in the middle, and then a spark gap connects opposite polarities, one of the top plates to the bottom. When the voltage gets high enough to break down the spark gap, an extremely fast discharge occurs here. And along the length of that is where your laser occurs. And like I've said, what's unique about this device and makes it so easy to build is it doesn't require mirrors, and it doesn't require a vacuum pump. It will actually work on nitrogen in the air at atmospheric pressure. So you've got some profound things here that make the nitrogen laser very unique. It's in a class all by its own. Not only that, but you can actually use them to pump dyes. I've used these nitrogen lasers with nitrogen, not air, to make visible lasers using fluorescent inks out of Sharpie markers, believe it or not. So you can actually use this laser as a power source for other lasers. One other design that you can use that sometimes works better is the LC inversion circuit. I'm sorry, the charge transfer circuit. With a charge transfer circuit, notice that the spark gap and the laser electrode channel have swapped places. This time you've got the spark gap up here, and you've got the laser channel over here near the edge. You've got the dielectric in the middle, and you've got the bottom plate, and you've got the top plate. In this case, the top must be positive. The one with the laser channel has to be positive. An inductor is optional here, but it really works without an inductor. What you do is you connect the positive power here. When the voltage climbs high enough, it discharges through here, quickly charging this capacitor. When this capacitor charges, then of course the laser channel is energized and you have laser output here. The one thing that's different here is this side right here is much bigger than this side. You want about 3 times the size capacitor here than you have here, so that when this capacitor discharges, it quickly overwhelms this capacitor, and it's a lot more energy in this capacitor, and then it causes a really rapid discharge over here. In some cases, this kind of circuit works better than the LC inversion circuit. And in the absence of an electronic power supply, honestly, this is a nice thing right here. if you're wanting to do a proof of principle laser. But if you're wanting good performance, you may need something like some serious high voltage. Well, one of the things that is surprisingly simple and is a source of amazing, almost unlimited voltage, not unlimited literally. It comes as a surprise, but you guessed it, static electricity. That's right. It's possible.
Jarrod, before you get on to that, we have a question from the audience, which is the direction forward, and which direction is forward and backwards. So it's going back a couple of demonstration diagrams ago. Alan, if you want to clarify that question a little bit, it's let's go back to the previous diagram.
He's asking which direction the laser goes, the laser light. Is that what he's asking?
Is that the question? Oops, I got the laser light. Yes.
Okay. Yeah. Okay, I'm glad. That's a very good question. Okay, the laser beam actually comes out both ends of the channel, but I found you can put a mirror on one end, a totally reflecting mirror, and you'll get a lot more power coming out the opposite end. Okay.
Even with the mirror just on one side.
Yeah, exactly. You can get a laser beam out of both ends, or you can put a mirror on one end and get a combined. It's like 250% more powerful coming out the other end. The other thing you can do, I found through trial and error, this is one of the things you may not read that much about, but if you actually slightly, ever so slightly taper the channel, and this is one of those very fine sort of things you can't put into writing, you just have to tweak it. If you taper the channel ever so much, I find that the wider end, most of the laser energy is concentrated towards the wider end. Now, there's some theories as to why that may happen. And there's even probably some, a lot of people that may agree or disagree. I personally think it's possible you could have a traveling discharge. And what that means is the discharge may actually begin at one end and move at the speed of light towards the other end, so that the amplification actually follows the electric wave as it moves down there. But regardless of what causes it, that's just one possible theory that I have. If you actually make one end just a little bit narrower than the other end, you actually get most of the light energy coming out the wider end.
Jarrod, I don't know if you're going to get to this later, and if so, just tell me so. But can you talk about the actual amount of power that's being created and why you have the channel there and how long it has to be, or why it has to be a particular length?
Yes, the channel can create a laser output. Probably the shortest I've ever done was maybe 4 inches. I don't know, but it's possible to maybe. I've seen people do them even shorter. If you get them too short, though, here's the problem. You're going to have mirrors, because remember, your gain is high. That's why you can get away with no mirrors. But the shorter you get it, your gain occurs along the length. The more your gain is a function of unit length. So if you make the laser too short, it's either not going to work, or you would have to have mirrors before it would work. And then that completely does away with the advantages of building this kind of laser, other than the fact that it'll work at room air. It works at atmospheric pressure. The other thing about the power, I believe that was the other question.
Yeah, how much is it putting out? Yeah.
What's that? Okay.
Yeah, how much is it putting out? Yeah.
Okay. Well, I calculated in one of my videos that you're probably assuming that the capacitance, and I forget the exact numbers. I think I calculated it was something like 150 microjoules. It's hardly any energy at all. But when you look at the power as a function of time, power is energy divided by time. The fact that the time is so short, you're looking at, and I forget the exact numbers, but you're looking at 100 and something thousand watts. But just remember, keep in mind that lasts for possibly 1/1000th of a second or less. So the average power is just almost nothing. I mean, the average power is very low, but the peak power is tremendous. And it's that peak power that's used to do things like pump a die. It's also peak power in pulse lasers that's used to do things like cut through diamonds and stuff like that. See, pulse lasers are different from continuous lasers. With a continuous laser, you can burn through something slowly. With a laser that is a pulse laser and has a high peak power, you literally ablate substances. You can, just completely, and you can vaporize things like tiny holes through diamonds and stuff like that. This laser won't do that. I'm just using that as an example. This laser exploits the peak power capability that it has rather than the continuous power, because the average power is very low and the continuous power is non-existent. It only operates in pulses.
Right. So now, was that pulsing every time the spark gap sparked? Was that?
Yes.
And so
yes, that is correct.
So it would take that long to. Now, what was the limiting factor there? Is how long it could build up the charge? Or,
yes.
Yeah. So if you had more power, it would cycle more often?
Yes. If you had a power supply that generated more current, it would pulse at a much faster rate.
And that brings us right back to where you're about to go. So I'll turn you back to your static power generator there.
Oh, yes. Peak power is, of course, remember that the formula for energy of a capacitor is 1/2 times capacitance times voltage squared. So because the voltage is a square function, you can get a lot more energy more easily, quicker, however you want to look at it conceptually, more easily by increasing the voltage rather than just trying to make bigger capacitors. For one thing, the bigger the capacitors are, the slower the discharge is. So you're limited somewhat in doing that. Well, what I found is I could get some really good lasers that had a lot of power by running them off of static generators. We're all familiar with the Van de Graaff machine. Some of us are familiar with the Wimshurst machine, but mine have primarily used Wimshurst machines, and they've used motor-driven Wimshurst machines, because with a motor-driven Wimshurst machine, I could get a relatively high current by virtue of the speed that the discs were turning, and it actually became a practical power supply, and I've done a lot of work with that. This is an example of a Wimshurst machine. It's very, very small. It's just a little Tinker Toy size one. I don't know if you can see the spark jumping across there or not, but it makes a little spark jump between the gap. But it's a mechanical machine. I don't know if you can see the spark or not.
I heard
it's a mechanical machine that generates high voltage electricity, but it's very low current. But if you were to build one of these machines, and I have, and power it by an electric motor, and it was a larger machine, you could get enough current to power one of these lasers, and you could make the spark gap much wider, which means the energy is much higher, which means you could get much more powerful pulses. The frequency wouldn't be high. You would be waiting every 2 or 3 seconds for a pulse, but you would be getting high peak power.
Okay. Let's see. You lost me there because I was admitting somebody. So hang on. So why is it slower? Or why do you get fewer pulses?
Well, because a Van de Graaff machine or a Wimshurst machine puts out a few microamps. Whereas if you have a power supply, like an electronic power supply, the electronic supply is going to put out a few milliamps. So you're talking about 1,000 times more the current. That's the difference. But here's the problem. Electronic power supplies are dangerous. If you were to hook a neon sign transformer up to this thing, you could be electrocuted, and it's potentially very dangerous. What I've always enjoyed about using static machines like I've never used a Van de Graaff. Most people are familiar with that. But using a static machine like a Wimshurst machine or something, one of the advantages of that is that it's relatively safe. You don't want to use any kind of high voltage around somebody with an electronically implanted device like a pacemaker or an insulin pump or anything like that, because of the radio waves that are given off by it. You don't want any kind of high voltage around someone like that. But the static machines are safer than a power supply that puts out a lot of current. The trade-off is that you get much lower frequency of pulses per second. You have to wait 3 or 4 seconds to get a pulse instead of getting 10, 20, 30, or 100 pulses per second. So it's a trade-off in average power, if that makes sense.
Okay, we have a question that not following where the actual gain comes from. Is it the spark? Is it the spark is bouncing between the reflected plates? So I don't think he gets quite where the spark is between the spark gap, but how is the actual lasing mechanism happening? So the gap between the plates you get that zap of power coming in. What's happening to the nitrogen that causes the lasing? I hope that's the question.
Okay. I'm glad it's very good question. I'm glad you asked that, and I'll show you what I'm talking about. This laser actually has 2 spark gaps. One spark gap is a normal spark gap like you would have on a Tesla coil or any other kind of science project. I hope you can see this here. Well, here's my camera right here. And as you can see, you have 2 brass nuts that are facing each other there, and they're a few millimeters apart, maybe 3 millimeters or so. And when the high voltage climbs high enough on the capacitor, it breaks down and goes through the air. And when that happens, another spark occurs, but this spark is along a linear channel that has a length on it. And there's air in the room, and the air, of course, is between that channel. And that's where the lasing takes place. But because that channel is long and narrow, light is able to be amplified in one direction along the length of that spark. Now, to call it a spark is a little bit of not quite doing it justice. It's more complicated than that, because you actually have the gas being ionized there, and you have an actual discharge. You see sparks, but it's not really a spark, just a hot spark like you have in a spark gap. There's actually a blue discharge that you could probably only see in a dark room. And so it's actually a discharge like you would have in a low pressure gas or a neon sign. But the difference is there's a lot of white sparks in there. So because it's at atmospheric pressure, a lot of people, it looks like a spark, but there's actually a preionization that takes place, and it's actually a true discharge in there. But to answer your question, the reason you get a laser light out of that is because it is all along one length. And so light can travel along that length and get amplified as it passes through that energized gas through which that electric current is jumping through, when it jumps from one channel right here to the other. Does that make sense?
So let's see if I have this right. In a laser with mirrors, the kind that we think about, you've got light traveling back and forth and getting amplified
Many times.
But in this one, it's really, and again, I'm not quite clear on this, but it's getting generated at one end and amplified along the length.
Correct.
As it travels, more power is ionizing the gas there essentially and putting out a photon, and those photons are
the charge.
Each individual photon being itself raised to a higher level, or more photons being generated? This is where
the nitrogen gas is being excited so that you have a population inversion. But give me one moment and let me show you something to clarify this a little bit for you. Okay, this right here is a helium neon gas laser tube, okay? And on one end of this tube, you have a mirror, and on the other end of the tube, you have a mirror. An electric current travels down the length of this tube. It's like a neon sign. And when it does, the light travels along the length of it, and it gets trapped between these mirrors. And as it bounces back and forth, it becomes amplified. It passes back and forth hundreds and hundreds of times, each time getting stronger and stronger and stronger and stronger. And that's the only way you can get a laser beam, by letting a tiny fraction of it, maybe 1%, pass out this front mirror right here. And that's how this laser works right here. It has extremely low gain, but it will make a continuous beam, a very weak continuous beam, but it's a continuous beam. With the nitrogen laser, on the other hand, you can't run it continuously. There's a reason for that. Okay, the first reason is that the peak current that would be required to make it run continuously would melt the thing if you could put that much current through it continuously. That's the first reason. The second reason is, and this is really weird and unique to this laser, there are many lasers that will only work pulse. There's probably more pulse lasers than there are continuous lasers. We only see the continuous ones in everyday life. But this pulse laser is kind of unique, even among the other pulse lasers, because what happens is called bottlenecking. You have an upper state in the atom, or in this case, it's probably a vibrational state, but I'll keep it simplified. You have an upper excited state where most of the electrons are at. I'm going to use that analogy here. And it has a shorter lifetime than the state that's normally below it. Where in most lasers, you have the opposite situation. You have an upper state where all the electrons are excited and the lifetime of that state is much longer than the state below it. What happens in this laser is as the electrons start falling and as a photon comes by and it stimulates the emission of another photon and makes that electron drop down to the next state, eventually you have more electrons in the lower laser level than you do in the upper laser level. And so then when photons hit another atom that's in the lower laser level, it re-excites the electron back up to the upper level and reabsorbs the photon. So in effect, what happens is the laser actually becomes black or opaque to its own wavelength after a very short time. So because of that limiting factor, this laser will only operate in pulses. It's impossible to operate it continuously. And so if it wasn't for the high gain, in other words, this laser right here has very, very low gain. That's why you got to have these mirrors on the end. If it wasn't for the high gain, it wouldn't exist. I mean, you wouldn't have a laser because getting a laser beam out of it would be impossible because it has a self-limiting factor that limits it to very short pulses. But it just so happens the gain's so high that in that short length of time and in the short distance light can travel, you can actually get a laser output. By the way, a light beam will only travel about 9 inches in one nanosecond.
Okay, we have a question that came in. I have and says I have an old neon transformer on hand. It gives about 20 kilovolts. Makes a nice Jacob's ladder. Could I use that as my supply? I think the answer is if you're willing to risk your life, right?
Well, my first question would be how much experience you have with high voltage. Neon sign transformers can be used to power these because what happens is the frequency is low and the current is high enough to where you can actually charge and discharge this capacitor between peaks and you don't even have to rectify it. And Neil Steiner has a video on YouTube that shows how to do that. You know, he shows an example of a nitrogen laser. My recommendation to you, however, would be to get online and do a lot of reading and look at a lot of videos and get your feet wet first with using the neon sign transformer. Get to where you're comfortable and familiar and, you know, where you have the skill to competently use that high voltage source safely before you try to apply it to something like this. Once you've got experience using the neon sign transformer and you get familiar with high voltage, its behavior, and you understand the safety guidelines behind it, that's the most important thing, then you might try using it for something like this. I cannot emphasize safety enough. Laser pointers, we'd stick batteries in them and they work off a few volts. But when I was growing up, there were no laser pointers. And most of the deaths and the injuries caused in the laser lab was not caused by the laser beam. It was caused by the high voltage. The high voltage is deadly. And a neon sign transformer at that voltage, even though it's current limited, is instantly lethal if you come across the output. So I cannot overemphasize the safety here. If you don't have experience with high voltage and you haven't done something like this before, no, absolutely not. I would tell anyone, unless they have unless they have adequate experience with high voltage and they really know what they're doing and they can safely use it and they have, you know, they're sufficiently competent to use the high voltage to apply it to other projects for other than what the transformer is designed for, I would say absolutely not. The other thing is, if you use a neon sign transformer and you really have the, I don't know what you call it, the education, the skill, the ability to use one safely, it better be an iron core transformer, because if you use these electronic solid state kinds that are around today on some of the more modern neon signs, if you hook them to anything that they're not, other than the load that they're designed for, which is a neon sign, it'll kill them immediately and they'll burn up.
Yeah, in fact, Matt, if you were going to say something, sorry, I just muted you. You can unmute yourself. But I mentioned that last month we had a presentation from Jay Bowles on plasma, and we talked about using high voltage and neon sign transformers and other stuff. That recording is available on our meetup page. I suggest that you watch that, and he says the same thing. Unless you really know what you're doing, this stuff will kill you. But there's a lot of interesting things you can do with a neon sign transformer, if you know what you're doing, and if you don't, it also will be interesting, but not in a good way. Well, go ahead, Jarrod. Why don't you continue there?
Well, I was just going to say that with the high voltage, I can't overemphasize the safety issue, and you have to. And if you don't have experience with high voltage, this is not a place to begin. You know, it really isn't. And I mean, so just that's one thing you want to consider. Always be safe, no matter what. Put safety first, because you can't. You know, that's got to be your primary goal right there, is safety. So I don't know what else to say. I just can't overemphasize it.
So I want to come back to laser safety too at some point, but just talking about your $3 power supply that you get on eBay, how dangerous is that when you drive that off of batteries or a 9-volt transformer or something? I mean,
well, you know,
you don't want to touch those ends, right?
Dangerous is a relative term. Let me tell you this. I've hooked this thing up to xenon camera flashes, and it will run them virtually continuously, and they get so hot you can't touch them. So yes, they're dangerous too. This static machine I just showed you, if you hooked it up to capacitors, it could be dangerous. You know, you don't want to take a chance with anything electrical, but when you start dealing with current electricity out of the wall, you know, where you've got unlimited current, I mean, you have to know what you're doing, or you have to have a lot of guidance from someone who knows what they're doing. You know, work with somebody else who can, you know, I guess you could say guided experience, someone who can help you through it and give you a lot of guidance and that sort of thing, because you just don't want to go into anything like this blindly. I mean, for the same reason, I wouldn't try to go up and fly an airplane just to try it out and see what the experience is like without knowing what I'm doing, because I'm going straight down and I'm going to crash. So this is not something that you want to start messing around with if you have no experience with high voltage and you don't have the kind of enough experience to know what you're doing safely. The other thing is, if you do know what you're doing, it goes back to what I was saying a while ago. This is like building a Tesla coil in the sense that you have to have one of the old iron core transformers. You can't try these modern electronic things, because those things will burn up. They won't last. They're designed to be hooked up to one type of thing for which they're designed for. And if you hook them up to something else, it's just going to kill them. You've thrown your money away.
Yeah, in fact, this is something that came out in Jay's presentation last month, was that one reason he likes the old spark gaps as opposed to the modern Tesla drivers is that the spark gap is undestroyable. I mean, just you can't hurt the darn thing. Whereas the modern stuff, you know, I have a little Tesla coil kit here that my wife bought me for my birthday. I haven't assembled yet, and I know if I do one thing wrong, it's just gonna pop up and explode, right? Because it's just cheap electronics. But Dan is expressing some concern about the hyper focus on safety. We're all adults here, he says, but and we all understand the risks, but I'm not sure we do all understand the risks that not just for the high voltage, but what happens to your eyes, you know? I mean, so talk a minute about this particular beam, what would happen in your eyes. And we know in general, not a good thing, but you're not wearing safety glasses at this, you know, when you did the demonstration. How much, you know, what would be effect of this beam? Because it's very short. And then when do you start getting, you know, if you did use pure nitrogen here, would it start getting dangerous? Anyway, go ahead on that, if you don't mind.
Well, if I understand your question, you're wanting to know how dangerous this is and what a difference it would make if you were using pure nitrogen. Okay.
Yeah, at what point?
First of all,
really, yeah, go ahead.
I mean, I guess you could say in a way that this right here is like a BB gun compared to a high-powered rifle. If you compare it to a neodymium YAG laser or a ruby laser or something like that, that would blow a hole through a piece of steel. But you have to treat any laser like it's dangerous. And the problem here is that you have a lot of peak power. And even though the energy is very low, it's that peak power that's going to ablate a tiny bit of a surface when it's focused on it. And that includes the retina of your eye. Now, if you pump a dye laser with this, and believe me, I've made lasers out of marker literally the stuff out of Sharpie markers, those yellow gunk out of Sharpie markers. You focus this on there when it's, especially if there's nitrogen in it, and I'll get to that in a minute, and you're going to have a visible laser beam. And I've seen videos and examples where the camera has a bunch of little spots all over it where the pixels have actually been burned out by that little dye laser. And there's a pulse that lasts a billionth of a second. Keep something in mind. If this thing was as bright as a pointer, your typical laser pointer, your dazzling little green laser pointer that looks like a lightsaber, but your green laser pointer could be switched on for 1 nanosecond, 1 billionth of a second, you'd never even see it. You'd never see it because that's too short a duration for that power level to even register. Your eyes would never see it. But the fact that you can see this demonstrates that there's a lot of power there. It's just a very, very, very brief pulse. And you don't want to take a chance shining anything like that in your eyes. However, when you're dealing with other lasers, you have a highly collimated beam. When there's mirrors on both ends, the beam's a lot straighter and it doesn't spread as much. And that means it can go further with less divergence. And that means it'll also probably focus very easily in your eye at a great distance. And so any laser should be treated with all the respect that you would treat a firearm, because once it goes into your eye, it's going to damage the retina of your eye. And there is no way that they can repair. You've only got 2 eyes. And many of the laser projects I do, I use the camera to be my eyes because I can replace cameras. I can't replace my eyes. And so you just don't want, or you want to have safety glasses that are adequate for the laser. You just don't want to take a chance with it. This small little demo device right here is okay the way I'm doing it. But, you know, if I was going to do a lot of stuff with it and be examining things up close or have it shining on a surface other than just a piece of paper, I would probably want safety glasses. Yes, it's better to have safety glasses. I'm not wearing safety glasses for this little proof of principle demonstration here, but yes, it would be better. I will say this too. Another thing is the nitrogen laser wavelength. Oh, I don't want to speculate too much on this. Yes, I should be wearing safety glasses. I'll just leave it at that. But
yeah, we have a couple
when you put nitrogen in there, it's a lot more powerful.
Yeah, so a couple of questions came in. What are some specific safety tips, both for the high voltage and for the eye protection? So one thing you have to do is you have to know your wavelength and make sure that your safety glasses match that wavelength. But I don't know if you have anything else you want to say about this particular setup and safety with the high voltage.
Yes.
Yeah, so go ahead.
Well, yes, if you put nitrogen in this thing, I have a top or a cover I put over the top of this, and I think I've got it right here. I have this little cover I put over it, and as you can see, it's got a hose barb on the top, and it sits right on top of there like that when I move the inductor out of the way, and I weight it down with something, and then I bleed nitrogen, like welding type nitrogen in there, you know, something that doesn't have any flammable gas, obviously, just pure nitrogen in there. And you have a profound increase in output, tremendous increase in output, a lot more power. And if you're going to do anything with this laser, like pump a dye, even a homemade dye using Sharpie ink or something, you definitely want the nitrogen. However, keep in mind that there are no mirrors, and this is a real short channel, and it's super radiant. So the beam is very divergent. It's not like the beam from your pointer. It spreads a lot with distance.
So, yeah. And is it coming out both ends of that too? Right.
Yes, it is, but I actually tapered it a little bit so that more of it comes out the end that you're actually, the business end that I'm showing you here.
And then if you put a mirror on that, like you mentioned, it would affect only be making 2 trips at the most, or
it would be making 2 trips.
Yeah.
Yes, it would actually have 2 passes at the most, and you would get like a 250% increase in output.
250%. Then someone's asking how much, if you go to nitrogen, how much more do you see out of that?
Well, at least 10 times more power.
At least 10 times. And if you did nitrogen with a mirror on one end, now you're talking some serious problems
You're
here.
talking about some serious power. You're going to be able to take a fluorescent liquid like a laser dye or even something. You can make homemade laser dyes out of laundry detergent and out of, I've even lased a piece of plastic before. You can make it out of Sharpie markers and different stuff like that. You can make a homemade laser out of almost nothing. And when you have the nitrogen in there, you're going to be able to create a visible laser beam. It's quite amazing. It really is, to actually create a visible laser beam out of junk.
Yeah, so let's see, we have a question about the tapering. Now, how much? And I know you said you kind of had to mess around with that, but is that like a 1% or, yeah? To
be honest with you, this is one of those things that you just have to, to me, I've never actually made the measurements. I just play around with it. I've done this enough to where I can just throw it together without really thinking about it. And unless I've overlooked something, it usually works first time. So it's one of those things you just get a feel for. YouTube and the web is ripe with examples of people building these, but it's one of those things, it's so simple, but it's like riding a bike. You got to kind of, once you learn how to do it, then, now I see how this works, but it may take a while to kind of actually get one to work the first time, because if the channel's too wide or too narrow and that spark gap is too wide and too narrow, it's not going to work. So to me, it's just finding a sweet spot. I get it. And all of a sudden the little spot appears at the end of the channel on that piece of fluorescent paper, and then you've got it. And then everything since then is little adjustments,
Okay. So can you change the subject a little bit? You talk about the dye laser and using this. Can you talk about what the setup would be on the dye laser? So you've got dye that you pulled out of a Sharpie or whatever, and there, do you put in a tube or mirror? What's?
Well, I'd be glad to talk about that. Let me find my little dye cell here real quick. I can't find the actual one. I don't see the one that I've made offhand, but I do see the lens. And what I did is I went on eBay and I bought me a little, no, I take that back. I got this off of, what do they call it? Surplus shed, but it's what's called it's a cylindrical lens. And if you look at it, what you notice is it's a lens that's long instead of round. It's like a long lens, and it's plano convex. It's curved on one side and flat on the other. But what it does, instead of focusing light to a spot, it focuses it to a line. And then what you can do is you can get your dye and put it inside of a little, now I make my boxes out of microscope slides. And you put RTV silicone on there, because if you try to use JB Weld or something, the alcohol will dissolve it. I found that out the hard way. Another one of those lovely things you only learn through experience. But you can do the microscope slide box. But what you want to do is you want to get a box and you want to have clearance because what's going to happen is you're going to have a dye in there that's concentrated sufficiently to where most or all of the pump beam from the nitrogen laser is absorbed right on the inside surface there. And then it's super radiant, just like this. The gain is so high, you don't have to have mirrors, and you actually have a laser beam coming out of both ends, a visible laser beam. Now, like this one here, you can orient it different ways and turn it different directions, and you may get more of the laser light coming out one end than the other. It is possible to do that, but you get a laser beam literally just coming presto out of a little container of liquid. It's an amazing thing. It's an amazing thing, seeing a laser beam actually coming out of a liquid almost. But you have to have a lens like this to focus that nitrogen laser beam into a line on the surface, because what you're doing is you're focusing the light and increasing the power density or the intensity into a nice little line. And then amplification takes place along the length of that line, just like it takes place along the length of this channel. Except your line in this case is going to be a few millimeters long. But the gain is so extraordinarily high that in many cases you can get a laser output without any mirrors, a visible laser output.
And if you were going to put a mirror on, that would be on each end of that box, and that would amplify it again.
Yes, I considered putting mirrors on it. A mirror on one end makes some sense, but I considered putting, well, it is kind of a problem because you've got reflections from the box itself, and that kind of serves like mirrors, and you have to kind of line those up. It's kind of fussy, it'd be so small. But the problem with putting mirrors on both sides is that the gain is so high, and that the output mirror would have to be so low in reflectivity, almost like a piece of glass, that I don't think there's a lot to really be gained from it. I think having one mirror would help a lot, but I'm not so sure you're going to see that much more by putting two mirrors on it. I mean, Mark Shello's website, The Professor's Home Built Lasers. I highly recommend going to his website, The Professor's Home Built Lasers. Mark Shello, and in Canada, because he has a real good website on dye lasers, nitrogen pump dye lasers. One of the best websites I've ever seen. Yeah.
Yeah.
Google The Professor's Home Built Lasers.
Okay, I'm going to put that in the chat.
Yeah, The Professor's Home Built Lasers.
Yeah.
Yeah, he has got an excellent site.
And let's see, there we go. Now, you've built a number of lasers. Can you talk about some of the other ones? Maybe how you got started, just kind of moving off of this one for a moment. What were some of your more fun lasers or beginners? I know you built a CO2 laser. That's a good start. Or another challenging project. Maybe just talk.
Well, in the early 80s, I had read about the CO2 laser, a high power gas laser. And you got to remember at that time, there was no laser pointers around, and, lasers were something that were somewhat of the stuff of fantasy. And I read about the CO2 laser gas laser, and I would always, CO2 gas laser, I would fantasize about building that. And I read in a book in the library, I'd go to the library and read books about lasers. I read that one of the researchers, this is probably dates back to the 60s, because the books I was looking at then were from the 60s. And he said one of the researchers, he even lased his breath. Well, when I started building my lasers here, probably around 2000, when I built the first CO2 laser, probably around 2008, 2009, I don't remember what year it was. John Singer recommended, he said, you ought to try lasing your breath. I said, you think it's got it's like, I don't know if that's got a chance of working. So I kind of came to the conclusion that I want to build my heart rate up so the exchange of carbon dioxide is maybe a little faster. And so I did a bunch of jumping jacks and got myself working up a sweat, and inhaled into a balloon and bled the balloon into one of those lasers. And I was actually able to get a laser beam out of that thing running off my exhaled breath. And that was a real novelty, I guess you could say, to do something like that. And but most of my lasers, to answer your question, have actually used a mixture of baking soda and vinegar. And you can look on YouTube, look under Gilligan's laser, how Gilligan would have done this if he had been trapped on the island, maybe with a little help from the professor, and he had no technology, no science, nothing else. How could he have built this laser? And this is called Gilligan's laser. And you can find that on YouTube, along with all my other videos. And but yeah, most of my CO2 lasers have actually used a mixture of baking soda and vinegar to generate the carbon dioxide. And then the carbon dioxide was fed through the glass tube. And when electric current ran through that gas, it would generate a very high power laser beam. And the laser beam could actually, the beam is like microwaves. It's totally invisible. When it hits a rock, the spot on the rock lights up like a filament on an incandescent light bulb because it's white hot.
All right, I found a link to that. I'm putting that in the chat group. This is great. So you've been talking for about an hour now. This is great. If there's anything in particular that you want to say, add on, that'd be great. And I'd like to open this also up to any additional questions that people might have. And
one thing I would say, if you seriously want to pursue a laser, you might get in contact with me, and I can tell you how to avoid making some serious, expensive mistakes, because there's a lot of stuff you can buy on eBay that won't work at all, especially if you want to build a ruby laser.
What's involved with building a ruby laser, and why do people do it?
What's that?
What's involved with building a ruby laser, and why would someone want to do that? I mean, it's the class, that's where it started, right? But
because a ruby laser will blow a hole through a piece of steel, it's super powerful. And it produces a visible beam. Go on my website and you will see many, many pictures of my ruby laser in action. It comes as close as possible to looking like James Bond. It really does. But if you want to build a ruby laser, there's a right way and a wrong way to do it. The wrong way is to get on there and spend hundreds of dollars for something that isn't a ruby. And maybe the person that sold it to you really doesn't even know it's not a ruby. The right way to do it is to get on there and wind up spending $20 for something that's a ruby that they're out of their mind selling it to you for that price, but it's coming out of something that is no longer used. It's an obsolete piece of equipment maybe, and they decided they're going to get the junk out of the lab, and so they sell this little ruby rod to you for almost nothing just to get rid of it. So there's a right way and a wrong way to do it, and you have to know what you're looking at. You have to know what you're looking at to keep from buying something that's a total waste of money and won't work in a laser. You can't pop a ring out of your, you can't pop a ruby out of your ring and make a laser. It's not that simple. You have to have a certain kind of ruby to work in a laser.
And you need the half silver mirrors and half silver mirrors, yes, and the whole works on that.
Yes, right? Yes, but unlike this kind of laser, the gain is real high. It's not high enough to do this, but the gain is high enough to where you can get away with some mirrors that are not that specialized, and they don't have to necessarily be aligned that well to get an output. I've actually made mirrors out of polished copper, believe it or not. Yeah, and I've actually used pieces of glass for the output coupler.
Yeah, you've been doing this long enough that you've done a lot of experiments making almost anything that could laze, right? You've been in there doing it. Not
well, I've experimented with a lot of things. I've even tried to laze chlorophyll when I soaked grass in a monkey grass and some alcohol. But I've experimented with a lot. That's one of the things I wanted to do with a kid, was go dig every rock I could up and see if I could make it laze. But
all right, this is great. So from the audience out there, we've had a few questions. If there are any more questions, now's a good time to ask. But barring that, can we turn back now to the laser, the original nitrogen laser there, and just kind of go over again what the basic parts are and the layout, and maybe run it one more time just for the fun of hearing the spark gap go and seeing the little seeing the light. That's what we're here for.
Okay. Now I hope I haven't messed up the alignment here by taking it.
If it's okay to do it, yeah.
Yeah, but okay. Let me turn the camera around real quick. Okay, well, the laser is two strips of metal, and these are really two capacitors side by side. They're separated by a gap, and they're connected by an inductor. Now, you can also use a string of resistors. Why a string of resistors? Because your normal little resistor, a spark will jump right around it. So you don't, you want a string of several resistors. Resistors actually produce a better result in my experience, but I decided to use an inductor to keep it simple for this demonstration. But this is just a little wire. It doesn't matter how many turns it is, because the inductance has to be very low for this to work. And the rapid step of current is far too fast to go through those turns of wire. It's either going to jump across the gap, or it's not going to ever make it through that. So you've got the two capacitors here separated. It's like one capacitor. This one side is separated in two sections, or you can look at it as two separate capacitors to the common plate. But remember, there is a transparent dielectric here, a real thin dielectric that separates these two little metal strips from that bottom plate right there. And it has to be razor thin. If it's thick, your inductance will be too high and the laser will not work. That is absolutely critical, and that's the part that goes beyond the physical details. Then you're getting into the part that you can't see, that's highly theoretical, that's really beyond what I understand. I just know it from experience and from what I've read. But you have to keep inductance really high, because unless you could populate that upper laser level fast enough to get a nanosecond pulse out, your laser will never work. This is why this is something that they didn't build by accident. because you can't just stumble across it. You have to know what you're doing. So
in fact,
it
that
takes
brings us up to the question: who invented this, or how did this where did this come from?
well, the nitrogen laser, I think, might have been, and I may be wrong on this. I think the nitrogen laser was invented by a man named Hurd, and I don't remember if it was 64 or what year it was, but the nitrogen laser was just one of many lasers that were discovered after the first laser was constructed in 1960, like in May of 1960. So, you know, then came all these other lasers, the carbon dioxide laser, the argon ion laser, et cetera, et cetera, et cetera. Diode lasers were around back then, but they weren't, the performance wasn't good enough. They had to be operated like in liquid nitrogen or something. I mean, they weren't good enough and to be used for pointers like they are today. But anyway, you've got the two top plates here. One of the plates is connected to the bottom plate with a spark through a spark gap. And see, I've got some coins right there to kind of hold it up. And when that voltage up there gets high enough, a spark occurs right there. And when it does, it causes this plate right here to discharge into this plate. And it's too fast to go through the inductor, so it just discharges across the channel there. Now, I have one amateur scientist that told me he believes it is the pre-ionization that takes place on the surface of the dielectric that enables this discharge to occur uniformly along the length of that channel. And were it not for the pre-ionization, you actually could not have a laser. If you just had sparks there, it wouldn't make a laser output. And unlike this design here, the charge transfer, somewhat, you still have pre-ionization, but it makes it simpler because this capacitor here can be a doorknob capacitor or even a Leyden jar. I've done it with Leyden jars. Only this connection here has to be low inductance. But with the design you're looking at right here, this right here, these both have to be very low inductance capacitors separated by that razor thin dielectric. And then you have the bottom plate, top plate, but it has to be very, very low inductance right there. And when I say razor thin, I'm talking about like 0.0. These are right on transparencies. You know, some of them are used like on overhead projectors where they write on them and shine the light through them, but they're like 5 mils thick, you know, 5/1000ths of an inch thick. So they're very, very, very thin. And if the voltage is too high, you'll puncture them. In fact, with the static machines, I've actually blown holes through the dielectric, and it actually blew a hole through the metal, you know. But you can make them out of aluminum foil. You know, if in fact, you could increase the area of these channels right here. I'm just using the actual area of the channels for the capacitors themselves, but I could make this thing larger and actually put aluminum foil under here and extend it out on both sides and scale the whole thing up larger and get a lot more power. I didn't choose to do so here, but had I done so, it would have fired at a lower frequency, but these little spots on here would have been much brighter. That's the difference.
There you go. So I only heard one crack, but we're still seeing that spark is going. So we don't always hear the crack of the spark.
Yes, a lot of the light, because it's so fast and so brief, it falls between frames on video. I'm not a fan of video. I like photographs, but I find that with video, it doesn't do justice because remember, the persistence of your human vision is like, I've heard that it's like 1/50th of a second. I forget what it is, but what it amounts to is when that pulse occurs for a nanosecond, there's a persistence of that vision that lasts longer than that. And so it looks like you could actually see it better in real life than you can on a video camera. And so for that reason, I actually enjoy photographing these things much more than trying to, if you look at my website, you'll see a lot of good pictures, but I prefer to photograph them rather than trying to, I don't know if I can click on the picture here and zoom in on it or not, but.
Oh, we can definitely see the beam though. We can see the spot.
No change?
Yeah, definitely. It's showing up very nicely.
Yeah, keep in mind that that's something that lasts a nanosecond. So the power there is really higher than it looks. And that's the danger of lasers, is that the perception often lies to you because you get the idea. When you look at a laser, you you go on your visual perception. Well, your visual perception is only as good as your eyes are detectable for the laser that's taking place. And if the pulse is very brief, it's not going to look as bright as it really is, given the peak power. In terms of peak power, I'm using the word bright here loosely. But also, if you have a wavelength that is only slightly visible, because see, the brightest color to the human eye is 555 nanometers in the green. That's why a green pointer looks so much brighter than a red pointer. Well, if you had a laser that was almost infrared, it may not look very bright to you. Well, the danger in that is that you would think there's not much power but there really is. Lasers, unlike an ordinary light source, the light is parallel, it's collimated, and so when it focuses it on the eye, it focuses to a tiny dot, just like a point source, and then it burns a hole through the retina. And once you burn a hole through the retina of your eye, there's no way they can repair that.
And we have another question here from Dan. Did you glue the aluminum strips to the thin film, or is it sitting on top?
No. Ideally, it would be better if you had weights on top of it. There are people that are a lot more adventurous than me that go and build things where it compresses it with bolts and everything. But with this right here, just the electrostatic force of the charge of the opposite plates is enough to make it stick on there pretty tightly.
Cool. All right. Great. Good. Well, all right. If there are any other questions, pop them in now. We've been talking for well over an hour. This has been fantastic. I have certainly enjoyed every minute of it. I hope everyone else has as well. Of course, I'm in a privileged position of getting to ask all the questions I want to know. But Jarrod, thank you very much. This is fantastic.
Well, thank you. Thank you, Ken. I really appreciate it. Thank you, Ken.
You're welcome. Thank you. I'll put the recording up. Well, I'll put it on YouTube and let you review it first, Jarrod. Then I'll add it to the website. I'll put the links that have come in through chat up there.
Also, don't forget my website. And you might want to give them the addresses to my website,
right,
jarrodkinsey.org.
There is on the meetup page right now, but I'll make sure everyone can see that as well.
Yeah, jarrodkinsey.org is my current website. There's an older one out there, jarrodkinsey.com, but you want to go to jarrodkinsey.org.
Okay.
And if you look up homemade ruby laser on YouTube, you're gonna find me pretty easy. I think my YouTube name is JK. I think that's what I've got on there. That's when you'll know it. I've got a lot of laser stuff up there if you want to look up my YouTube videos.
Yeah.
Now, somebody put me okay, there it is. Yeah, jarrodkinsey.org.
And
yeah, and feel free to email me if you want to. My address, Jarrod 694, Jarrod Kinsey 6. This is kind of embarrassing, but I don't do my own website address. I forget it, but it's Jarrod694@gmail.com. Jarrod Kinsey 694. I'll send it to you, Ken, and you can pass it to everybody.
That's good. I have it right here, Jarrod.
And I forget.
Yeah, I have it right here. And that's very kind of you to make that so available. I know that people like you and Sam. I haven't met John Singer, but very open and very supportive. Then there got some people like Styro Pyro. Watch out for him. He's way out there. But if you want some entertaining videos, you watch out for him. And safety is a real concern. You can take apart a Blu-ray writer and destroy your eyeballs in no time. There's plenty of instructions on the web on how to do that, so don't do it. But this is a neat project. I'm still very nervous around high voltage myself, but maybe once we get the makers group back up and running and the vaccine and all, we can get together with some people who know what they're doing and build one of these things. Because the actual build isn't too hard, so long as you're careful. And I look forward to actually doing that and making this work.
If you don't have experience with a high voltage, you can always use a static machine and it'll work. It's just going to take a lot more patience because you're going to get one pulse every now and then, and you'll have to spend a lot of time until you get it to work.
They're fun in their own right too. You can have a lot of fun with the Wimhurst machine anyway.
Yes.
Yeah. Great. So at this point, I'm going to call it quits for the night. Thank you so much, Jarrod. Thank you all for attending. I thought it was fantastic. Stay tuned for future presentations, and stay safe, everyone, and stay well and stay in touch. Thank you all.
Thank you, Ken.
Thank you,
Ken.
This is great. Very,
Okay.
very appreciated. Okay.
All right.
Over and out.
Bye-bye.
Bye now.